Good morning, I'm Louis-François, CTO and co-founder of Towards AI, and today we are diving into our second session of our 5-session course all around building on top of LLMs. In this one, we follow the classical path of any AI engineer going from implementing an LLM into its application to building on top of it with fine-tuning, RAG, prompting, everything you need to know and need to do in the right order. So it's a 2-hour crash course on what to do when you try to implement LLMs in your application. I hope you enjoy this free session available for you now on YouTube, and I invite you to check out the full course on academy.towardsai.net to purchase the last 6 hours of the course. Please go check it out to learn more. Also, I want to remind you, if you missed it, the first session is also available on my YouTube channel. Welcome to the second session of this course. In this one, we dive into building on top of LLMs. If you missed the first one, we covered the foundational knowledge and using LLMs. So it was a bit more of a theory recap, and we discussed the limitations and weaknesses, and most importantly, why does this course exist? We share a lot of tips, useful tips for using closed versus open models, prompting, benchmarking models, etc. In this one, we will focus on customizing and building around LLMs. And more specifically, here's the plan. We start with still a bit of essential theory, let's say. So first, we just do a small comeback on LLM's limitations. So the problem with context window, the knowledge problem, and more. Let me dive into that shortly. Then we talk a bit more about embeddings and encoders, what we can do with long context, RAG, CAG, fine-tuning, and finally, reinforcement learning. Then Omar comes in with a bit of practice with structured outputs and practical demonstrations implementing RAG, CAG, and fine-tuning. All the cool stuff. So let's start right away. LLM limitations. There are many of them. I guess the biggest one is hallucinations, when the model just invent stuff on the fly because it's just a predicting machine that's predicting words. It doesn't know about truth or lies, as we saw in the first session. And so there's a problem. We call hallucinations, maybe not the best word for it, but it just means that LLM is generating nonsense. A second limitation is the context window of models. While some models like Gemini give millions of context window, it's still not that performant. And as we saw recently, if you heard of it, Llama 4 had pretended to have 10 million tokens in the context window, and it wasn't performing so well. So anyways, we can scale to millions of context windows, but the models aren't performing that well at this range. And otherwise, there's a true limitation of skills and potential when you give more and more tokens to the LLM. So you always want to restrict it and give it the most essential stuff. So we will cover this in the course. Another limitation is that the knowledge you need is sometimes not present in the training dataset. If you want to ask questions in a different language or about a programming language that is proprietary to your company, might not be in the LLM knowledge base when it was trained, and so it won't be able to answer correctly. If you're not sure why, I invite you to check out the first course again, where we discussed the training of LLMs. Another limitation is the knowledge cutoff. So this basically means that when we train LLM, as we saw in the first course, the training ends at a time t, and after that time, you can serve the model to users. But then the model isn't updated anymore. So if the president changes or anything happens, it won't know about it unless you do some kind of fix, which is, for example, to give it access to internet and other things, which we will see in this course. But this is a limitation, an intrinsic limitation to LLMs, that its knowledge is fixed in time. Another limitation is the reasoning of LLMs. I'm not talking about reasoning models like O1 or O3 or O4. I'm talking about models not being powerful, logical machines. Like they are not conscious and humans. They make very dumb mistakes, as we saw. And so a very foundational limitation is their capacity to reason and understand the world. So solutions, well, first, we add knowledge. That's the easiest fix, I guess. And that can be done through many ways. And these many ways, we will cover them in this course and in what order we have to do them. Another solution is to control or steer the generation. And this can be done through many approaches as well that we will cover in the next hour. So what can we do to fix LLM limitations? Should we fine-tune or retrain, tune, do fine-tuning? There's many synonyms, but basically, just retrain our model. Should we do that from the start? No, never first. Why we never want to do that first? Firstly, it's because it's quite costly. You need thousands, if not millions, of examples of question and answers you want, because you are basically retraining your model to understand the language and the world in different ways. So you are not just trying to tweak a bit how it responds, you are rather trying to reshape its whole understanding of the world specifically to your needs. So it takes a lot of data, it takes a lot of time with experimentation to do that correctly, which means it's also super complex. You need to do that many times. There are training problems like failure runs where you need to restart or start from an earlier checkpoint. It's very complicated. Plus, it means you need expertise. You need some ML engineers, ML research scientists. You need to spend a lot of money and get the right people on board to help you do that. Another limitation of doing that from the start is that you become model dependent. And with such rapid progress that we see with all the state-of-the-art models, this is quite a big limitation because you stay fixed in time with, for example, if you fine-tuned Llama 2, you still have Llama 2, whereas Llama 4 recently came out and some other very great model, even open source models that are much better than Llama 2. So you need to retrain for every new model. It's even more expensive and complicated to do. Also, another thing is that the model might not be the problem. So if you do that from the start, you guarantee costs and wasting time, and you don't guarantee the results. The model itself may already be capable of what you want it to achieve, but with a little help. Here's what we can do instead of fine-tuning right from the start. So I will draft this whole first hour around this plot. So I will just take some time to explain it. But basically, there are two axes, four quadrants to represent the space of all possible solutions and things we can do. The two axes are from low to high, left to right, or bottom to top. And the y-axis, the one vertical, it is about external knowledge needed. Whereas the horizontal axis, the x-axis, is about the model adaptation needed. So how much you need to tweak the model itself to achieve what you want. So for example, if we ask, what is a transformer? The model already knows that. You don't need to retrain it to modify its weight, its parameters. You don't need to add external knowledge. It knows what it is. This is fixed in time. What a transformer is doesn't really change. But if you ask it, what is the current best LLM or current best transformer? Now this has changed since 2023 or whenever the model was trained. So you need to add external knowledge, whether it's like the top 5 query from internet or just your own database. You need to give it updated information so that it knows what is the current best LLM and then can compute and generate you a good answer. If you ask it to write it in a language that it doesn't know, then you need external knowledge and you need to adapt the model, because just giving it some information on the new language won't make it speak the new language. You instead need to really change its inner workings so that it can talk this language. So you need both external knowledge and adapt the model. And lastly, you might want to have the model write in a specific way, compliant to a specific norm or follow some kind of structure. In this case, you will not need external knowledge because the model already knows about this, but it doesn't really do it every time. Instead, you want to adapt the model to do it every time, but it already knows how to do it. So you don't have to really fine-tune each parameter of the model and really retrain the way it thinks. You just need to train it a bit more, a bit superficially. And what are each of these quadrants called? The first one, the basic one, is prompt engineering. The second one is our RAG quadrant, so giving more information, Retrieval-Augmented Generation. The third one is fine-tuning, the thing that most people want to start with. And the last quadrant is reinforcement fine-tuning that we will all dive into in the course. And just to show a roadmap of what we will do, here is the typical path of what each company should do when implementing LLMs in their application and in which order. So I will go over them very quickly, but just be reassured that I will go over them one by one with lots more details in a few slides. So this is just to show what we will do, but we will go over them in detail. So don't worry if it's a bit fast. So first you want to start with prompting, specifically zero-shot prompting. Then you want to try few-shot prompting, so giving it a bit of examples of how to do it. Then implement some basic RAG feature, more advanced ones. Try fine-tuning, but not the generator, the encoder. Then try fine-tuning a generator. And finally, fine-tune a generator again, but using reinforcement learning. But this was quite fast, and we didn't really explain what each of these steps mean. So let's rewind back a bit. We want to start with prompting. This means maximizing or leveraging the LLM's base knowledge as much as possible. This is because LLMs are extremely powerful, they know a lot of things, so why not try to extract the most out of it before we spend money? So how do we do that? First, we choose the model according to our needs. So the right model for the text. For example, if you have very long context and long queries all the time, you better use Gemini for now. If you have complex requests that will require several steps back and forth, follow-up questions, I'd ask a reasoning model like O3, for example. And then for more intellectually simple requests or like very basic questions, I'd try 4.1 mini or nano, Gemini Flash, or 4.0 mini, depending on where you're using the models. Then you want to optimize your instructions, your prompts. You want to refine them, test them on evaluations that you build, which we will see in the next course, and ensure you maximize the instructions. Finally, you want to maximize the context you are giving to the model in your instructions. That's another part that is done doing RAG, which we will cover shortly. But first, to optimize the context, you want to give the model a few examples of showing what you want to achieve. So for example, here I give it just 2 examples of how I want to translate text from English to French. And here, when I ask translate this text and then enter the English query, it translates it in French in the right format, just by sending it 2 examples. We recommend sending at least 3 to 5 examples minimally. Then you want to add the missing context from these examples. And to do that, you would have pre-selected examples added to the prompt of the user to enrich the prompt, send the LLM, generate the response, etc. So this is all from the 3 to 5 examples that you give. You add it to the context to add to the context. Next, you may want to adapt your examples according to the request of the user. Instead of sending always the same 3 to 5 examples, you may want to build some kind of JSON file or whatever type of mini database that you could host locally easily, and instead have a dozen, 20, 30, 50 examples and find the best examples to give to the user based on what they ask. So you again enrich the prompt, but you select the 3 most relevant examples based on all your examples in the question. So here, this is what we call the retrieval part. And there are several steps to find the relevant information in this retrieval For example, in our JSON, we want to find the 3 most relevant examples from the 50 we have. So how do we do that? Well, we have to understand the user's request. Then this user request, we have to translate it into a language the machine can understand. This is done using an encoder and embeddings, which we covered in the last course. But quickly, it's basically at this step where we send the transformer model. So after taking our sentence, making our tokens, and then making the embeddings, this is what we use to compare text. Why? Because it's our numbered representation of each word and of each concepts, meanings, sentences. So it basically allows the model to understand the sentence and the words and represent it in its own space. So here, for example, we have its space showing that cat and kitten is pretty close, whereas dog is a bit farther away. And so thanks to these numbers and this space, we can, since they are numbers and not just words, compare them to each other. This means that, for example, here, if we show the cat and kitten points, we see that they are much closer than cat and dog are. This means that if the user enters cat and you select the most relevant embedding that we have in our dataset, it would be kitten or cat if we allow to give back the same embedding, but otherwise it would be kitten because it's closer to it. So this is basically what we do. We use embeddings, so our vectors, because they are in the same space, the same language the model understands, and so the model can compare them. Then we find these most similar examples with approaches, with calculations like the cosine similarity, which is basically just, if we get back on these arrows representing cat and kitten and dog, it just measures the difference between them. So the distance between them, which in simple terms will be the angle between the two vectors. So this cosine similarity measures exactly that. Now, if we get back to our path, we have been implementing basic RAG. We are starting to implement that. We have a JSON with many examples, and we try to retrieve the most relevant ones in them. But basic RAG has obviously some limitations. For example, retrieval can become pretty slow with many examples. If you have a JSON with millions of lines and trying to compare all of them one by one to find the 2 most relevant, it will be pretty slow. You will also have to constantly maintain and update the JSON, read it with each request, etc. It's super inefficient globally. Also, you cannot have other types of data. You cannot have images, tables, and sounds or whatever from this basic setup. Embeddings are also not always the best way to find what we want. Sometimes we might actually want to find exact keywords like a specific name or a specific place instead of asking the model to give us information about different places, different people. That's just because we may want to have everything referring to someone specifically in our dataset or some concept, rather than just getting the most similar meanings, which won't guarantee us to have exactly this name get back to us every time. That's because embeddings understand the global context of the text. So if you embed a sentence, it will understand the global context of the sentence, but not the specific words or exact facts. For example, also, if you want only in your dataset the results of men aged 50 and above, you better use filters rather than trying to do that with an embedding. Or likewise, more general questions about the database itself, like how many clients do you have that like sports, or how many Python programmers do you have, etc. These could be done with just filters. The user's question doesn't necessarily have the context needed as well to find the useful data. This means that sometimes a user's question is ambiguous and doesn't really contain everything you need to know to answer this user, which means that you may need more detail and you need a more complex setup to ask it the details that you like. For example, if the user asks to give specific things for, again, men aged of 50 and above, well, you might want to ask how many of them, from what location, etc. Everything that makes this query ambiguous, you want to clarify it. And the solution to do that is to build some kind of more advanced RAG system, or Retrieval-Augmented Generation. So we are now here in our typical path. And the difference between basic and advanced RAG is basically that in basic RAG, we have on the left a user asking a question, then we retrieve the useful sources, add it back to the prompt, give it to the LLM, give a response. That's pretty much all we have. In a more advanced setup, it will rather look something like this. And we will go through all these steps one by one. So first, the data. We need to start with good data. Remove the junk with filters, small models, regex, or even ideally human review. So you check your data before preparing them and make them as good as they can be. After that, you perform the crucial steps, chunking the text, embedding the text, and putting it in your database. So chunking is basically just splitting your text into smaller bits so that it's best to give the model only what it needs and not additional context, which would add noise and make the model not able to answer or trump the model a bit. And there are many ways to chunk the text that you have as optimally as possible. And when I say optimally, I mean in optimal sizes. So you don't want to cut where it's in the middle of a sentence or in the middle of an ID, even if it has many paragraphs, etc. Basically, if it's too small, you will lack context. If it's too large, you will add useless noise. You generally want to keep your chunks between 200 to 500 tokens. It's a good compromise depending on the encoder and LLM you are using. And the most important part is that you test and evaluate and measure for all the different scenarios that you may have. So there's no one ground truth solution. It really depends on your data. You also may want to try chunk overlapping, which means to use an overlap of, let's say, 10 to 20% to avoid information loss between segments. So that means one of the segment will have plus 10% of tokens. So if you have 100 tokens in your segment, you will also take the next 10 tokens, and the following segment of 100 tokens will take the previous 10 tokens as well. So they will have an overlap of 10 tokens that goes to both segments, just to ensure that we didn't cut through something relevant for the context. Another thing we can do is intelligent segmentation. You don't want to cut randomly. You want to rather favor complete sentences, coherent paragraphs, respect the structure of the text. Then you can also use variable context levels, which is often called Matryoshka chunking and embedding, where you can do that at two levels. So here I say chunking and at the level of embedding, which means that at the chunking level, you would create nested chunks like sentence, embed paragraphs, then embed complete section, and do retrieval on the context levels adapted to the query. And that is all to retrieve context levels adapted to the query, finding the most similar information, which would ideally find the right level of information it needs. Then you can do that, this Matryoshka type of compressing with embedding. This is a bit more complex, but basically you would just have multiple encoders that will encode at various levels the same chunks. So one chunk would be, as we said in the first course, would produce an embedding which has thousands of values, for example. And instead of just having one with 1,000 value, you would have embeddings with 1,000 value for all your chunks. Then you will have another embedding with, for example, 100 value for all your chunks. Then another embedding with 10 values for all your chunks. If you have a huge data set, you can start with comparing only the 10 value chunks, finding the 100 most relevant, and from these 100, use the 100 embedding size or the 1,000 embedding size to just find the 3 most relevant chunks. So that's specifically to optimize the research process, but it's a more advanced feature. And while you are preparing your chunk, you also want to do other things in your dataset. you want first to extract the metadata or any information you may have about the chunk, add relevant context to these chunks, relevant information about the global document, main topics, or just synthetically generate section summaries or other relevant information that could help the model. And then you may want to do anonymization as well, depending on your type of data. Finally, after that, you want to embed your text chunks into embeddings. And for that, you use an encoder, either open source or private. Cohere OpenAI has great ones. You can use open source ones as well. After that, there's the research part. And as we said, retrieval with vector search isn't the best search method. Embedding comparison isn't the best search method. So you can do different things. The first one could be keyword search with techniques like BM25, BM42, etc. You may want to just compare keywords and find the same keywords in your dataset. The second one would be using filters, either by metadata or other type of data that you may have. Or then you can try embedding search, vector search, which we describe, that use two important things, the vector database and indexing. A vector database is just to store the embeddings efficiently, like ChromaDB, for example. It will save the text chunk and the embedding together for easy retrieval. It works differently from classic databases like SQL and NoSQL that use tabular structure. It really uses embedding, puts them in order, etc. It allows for scalability to millions of vectors without brute force comparison or comparing, which means comparing one by one each vector as we described in Basic RAG. And some popular examples here are Pinecone, ChromaDB, Waviate, etc. Then an important part is indexing. This simply means to group and optimize embeddings to accelerate research. This is always to avoid brute force search across the entire database to reduce latency. So instead of having, for each user query, having to compare it to all your database and then find the two most similar, you will have them in order already and just easily be able to know which one is more similar super rapidly. If we go back here, we have our embedding search, and the next step would be to try hybrid search. So combining keywords and embeddings. This would be super efficient. You take the three best documents for each and combine the results to have more information and the best one possible. Then you can add other ways to find information, like an agent connected to your SQL dataset, a CSV, a graph database. You can add whatever you want. And lastly, you can do an intelligent routing system. So adding them all together. Basically, here you will have another LLM, which we call a router, having specific prompts to orient the retrieval to the right type of retrieval. So if it understands it needs to find the most relevant exact words, it will use keyword search, for example. If it understands it needs very good structure to understand links between two entities, etc., it will use SQL or GraphRag. Or if it needs to understand the global context and just reply with a good answer, it might use just cosine similarity with vector search. So it does that intelligently, ideally. Now we are still here with the retrieval. And if we add our user, it looks like this. User, yes, ask a question. We do the retrieval from the database that we built. There's nothing new much here other than the whole data preparation steps. So what can we add? Well, we can improve those information a lot. So when we retrieve information, we can reorganize them, rank according to the quality of the retrieved chunk, reorganize the data to make more sense of them, which can also all be done by a model that we can fine-tune to do that. We also may want to remove duplicates or, depending on what we find, summarize the information if we have too much information in our chunks, or otherwise augment it with a loop to add more chunks and find more relevant information by searching differently in the different database or changing the request to find different responses. And then once we optimize the chunks that we receive, we can add it back to our prompt give it to the LLM, and provide the response to the user. But it's not over. First, we want to evaluate our pipeline and quantitatively improve at each of these steps. We don't want to just try these steps and implement them one by one and have this thing at the end without having tested beforehand. When chunking, we want to test when adding the re-ranker, when adding the summarization, when adding each of these steps. So testing, which we'll see in the next course, is crucial here. We also have limitations with this advanced system. There's no LLM to improve the retrieval itself. The user questions can still be vague and problematic here because it will retrieve nonsense. We do not allow for images and other modalities still. We may have difficulty finding the right chunks. We may have difficulty providing a good answer, even if we find the right chunks, like speaking a new language, for example, especially with the mini models that aren't so good at generalizing code to code. So, next, we might want to add a few things, a few interesting next steps for a real advanced RAG. And this is all, by the way, optional, depending on your needs. Again, you want to evaluate each step to know if you have reached a good point or you want to still keep improving the system. So the first thing we want to do is to incorporate a verification loop between the generator and the retriever. This is just to make sure that we don't fail at the retriever step and we give the best information possible that we have access to in our database to the generator. So we want to ensure that before the generator generates the answer. And to do that, we may also want to rewrite the user's query for better search context. So if the query is ambiguous, we may want to either automatically, based on our knowledge, modify the query and add the essential information before doing the search, or ask the user to refine, clarify, just like OpenAI's Deep Search does. If you've tried it, if you ask a question to OpenAI Deep Search, it will, I think in all cases, get back to you with questions to clarify what, if it has understood what to do, and ask for clarifications. You then may want to try new ways to retrieve and understand context, like GraphRag, for example, where you'd use that to manage global queries about your dataset to improve the understanding of relationships in your dataset and to extract and structure knowledge in different ways. So that's an advanced technique you can use if you see relationship issues when the model generates its answer. So if you see it didn't really understand everything between two things, either two personas or whatever, two concepts, you may want to use RAG to ensure you retrieve all the information that links the two concepts together. You may want to add modalities, which means adding image search, like using visual embeddings with relevant images. This can be done using a model like Clip to embed also images. So have embeddings of our images that can be compared to text embedding, textual embeddings. That's what Clip does. You may want to use audio and video analysis, either convert speech to text or transcript videos to use them in your text database as well. You can use structured data integration with SQL or CSV and generating charts via LLMs beforehand. You may also want to do an adaptation of your embeddings, choose specialized models like Clip, for example, to process or convert specific modalities from image to text or audio to text, etc. And we are now at this point in the graph, where after advanced RAG or during doing advanced RAG, you may want to start trying to fine-tune actual models. And here start with the encoder and our re-ranker here. And for example, fine-tuning the encoder means that the encoder would be able to have a better understanding of the domain. So here, I just have blue and orange, but to illustrate, I will give a specific example. If we are in the medical field, and I'm not an expert at all in the medical field, we may be talking about a specific illness or a specific cancer or whatever with very specific medical terminology. And if I hear them right now, I will just put them all together under it's something medical. So here, that's what we see on the left, where the orange and blue dots are a bit together. But to an experienced ear, like a doctor, they know when they hear a word, they don't classify it as just medical stuff. They classify it as, oh, this is related to the prostate, this is related to the tongue, whatever. They know what it means. And so they can cluster the topics in much better ways. So here, that's what we will try to teach our embedding model, is to do better embeddings by having him better understand the domain and thus create better groups of data that resemble each other, instead of just having like a global group of this is related to medicine. We would have a specialized medicine embedder, which in it would have groups for all the specialties that a usual specialist doctor knows about. So it's always to replicate the expert, and here giving the model expertise to a domain, if that's our current issue, would help with having the generator and the retriever and everything a better understanding of the answers as well, without having to fine-tune the generator itself yet. Then another thing we can do in this whole process, still in advanced RAG, would be to implement CAG, or Context Augmented Generation, context caching, which is, again, optional, but quickly, it's just a Boolean you turn true or false when you use an API, or you can implement it locally. But basically, it will just cache the embedding of specific things. So if, as we said in the first course, you ask a question about a report and you send the whole report to the LLM, and then you ask a follow-up question, you don't want to send the whole report again. It will just process the whole words, again tokenize, again do the embeddings, all before sending the actual model. Here instead, we will save the embeddings just before the attention layer that we see here, that we covered in the past course. And so the whole report will be already ready to process by the model. And the only thing we'll have to process is the new question that we do the tokenization, the embedding, and then we add it to the right of the report, and which is the query on the image on the right here, and we get our answer. So it's basically just a thing to make it much more. It's basically a technique to make the generation much faster and efficient. Then we may want to finally try fine-tuning. So as you see, it's not from the start, it's actually at slide 115. So it's quite down the path of improving the LLMs in your application. And when we say fine-tune our generator, our model, which is the model that answers the user, we mean to do that as efficiently as possible. Here in fine-tuning, we often just try to retrain the deeper layers. This is because it has been studied, and the deeper layers and transformers are the ones that understand the context and the sentence and everything more conceptually, whereas the first few layers focus on grammar, syntax, and more language stuff. And so we do this to add knowledge to our LLM, and this is all done ideally with a technique we call LoRA that we will see in the next courses, which is about fine-tuning LLMs efficiently, where we keep the same big, large LLM, the large language model, and instead we just use tiny adapters that would modify all the model without having to retrain all the model. We just train those tiny adapters. Anyways, we will see that in the next courses, but it's just to say that there are ways to fine-tune models very efficiently. And finally, if this still doesn't really fix all your issues, and there's still problem with UX and with the way the LLM generates answer to your users, you may want to try reinforcement fine-tuning, which is new to the OpenAI platform and other platforms, or reinforcement learning fine-tuning that is often called. And so this is mainly to improve user experience, as we say, because here, instead of retraining the model or adapters for the model to generate tokens in different ways, you actually retrain the model to speak in different ways, but with the same knowledge. We covered it in the last course quickly, and we will cover it in the next few courses. But basically, what we do here, instead of retraining to generate tokens one at a time and changing the way it generates tokens, you actually train the model again, but not per token, but rather per answer. So you give it examples of a question, a query, and a response, and then you give it a system to rate the answer, whether it's an LLM as judge or a specific calculation that you do, a function that you use, whatever. You give a rating to the answer, and this rating will be used to tweak the model's weights, the model's parameters. So you retrain it just once per response instead of for each token as done in regular fine-tuning. And so we've covered lots of things, but when do you do which one? Between RAG, CAG, using long context models, fine-tuning, reinforcement fine-tuning, using reasoning models, which we didn't even cover here because we will talk about it in the 5th course, which is available on the Academy platform. But quickly, here's a quick recap on when you want to do each. Typically, you want to follow the trajectory that we covered here, but quickly, you may want to use prompting for initial testing, or if you see the model already contains the knowledge you need, or if you just need to add a little bit of knowledge so that you get a good answer. You definitely want to just test and try it because it's super low in cost and easy to know if the model will be good enough or not. Then you may want to use RAG for larger database that you have and for faster response time and reduced cost, because you can use long context, send the entire code base or whatever report to the model, but this will use lots of tokens, increase the cost, and even add a problem because longer contexts aren't perfect and the models generate random things sometimes because of the needle in the haystack problem that we saw in the last course. So anyways, RAG is the most efficient system, but if you have, for example, a monthly report and you just want to ask 2 or 3 questions, you don't want to build a whole RAG pipeline about the report and repeat that each month. You can use a long context, but when you do that, try to use CAG turned on for when using a Gemini model or whatever, for example, just because it will save you money by pre-computing the report once, and then you can ask your question several times and it won't compute these embeddings every time. For fine-tuning, you may want to use it for very specific tasks. Also, if you have existing substantial dataset, because it takes thousands, if not millions of examples to fine-tune, retrain a model the way you want. And that's really to optimize performance or teach new domains. It's something you do at the end or in very specific cases. For reinforcement fine-tuning, that's actually super useful to improve the way you reply to user based on their feedback. And ideally, you do that with an already good fine-tuned model. You don't train one from scratch using reinforcement fine-tuning. You do reinforcement fine-tuning at the very last step of the whole pipeline. And also the plus here is that you don't need much data in this case. You just need, based on what OpenAI says, a dozen or hundreds of examples rather than thousands, if not millions, to have very good tweaks in the models and get very good responses in the style that you want. And for reasoning models, which we'll cover in the next courses, but that you probably have already tried before, you want to use them for more complex tasks, obviously, because they spend more token, they think before they answer. And that's also pretty good for multi-step and logical questions like math, code, planning, mostly because, as we will see in the 5th course, they were trained mostly on math and code to generate plans and have specific responses to follow. Anyways, we'll get back to that on the 5th course. You may also want to use that for when you need very detailed and structured explanations, when you need a detailed report or a very thorough response. If you know that you already need all those things, you can use the reasoning models right away. The most important thing, as we said, is to measure and evaluate everything. Prompting, RAG, long context. Just have a base evaluation data set and try it. Try everything, compare everything, and know what's best. Don't just try blindly. And we'll see that in the next course. Now, I leave Omar to cover structured outputs and practical notebooks for RAG, CAG, and fine-tuning. Since you are watching this on YouTube, please consider checking the full course on the Towards AI Academy, where if you liked this first hour, you can benefit from 9 more hours of useful concepts that are way more applied than this first foundational theoretical lesson. So if you enjoyed it, please check out the Towards AI Academy for the full course. Also, we offer consulting, coaching, and training, so please reach out to me either by DMs or to my email louis@towardsai.net for any queries or any questions. I'd be happy to chat. Now, let's get back with part 2.
Hello everyone. So let's start with the second part of this session, where I'll be showing a little bit more practical tips on how we can build on top of LLMs. So in this section, I'll be presenting what are structured outputs, why it's useful, and I'll show some code on how we can implement structured outputs. And then I'll go over some notebooks, so some code on how we can implement a basic chatbot that uses retrieval to answer questions, and some notebooks about context-augmented generation, and finally an example on how we can fine-tune a model, a closed source model. So let's start. So here we have an example of some text that can be generated by an LLM. And as you can see here, it's a paragraph, and if we had asked about specific elements in the text, here it's very hard to know if the model actually generated all the information that we wanted to see. So for example, if we wanted to generate a description of some people working at different companies, here we wanted to see the name, the age, the role of the people, and other types of information. And it's very hard to know if the model actually generated those elements. Here I highlighted the main points we wanted to see in the answer. And also the format in which the information is presented. Here it's within a paragraph, but the model could have put the same information in Markdown or in a JSON schema. We didn't give it the instructions to do so. So the model will kind of surprise us. We're not sure how the information will be presented and if all the information is actually within the text. So that's why we like structural outputs, because it's a way to manage these kinds of factors. And so what is structured outputs? Well, it's just a technique where we can make the models follow a predefined schema, for example. So if we want the answers to be within a JSON schema, or if we want the answers to be within XML, for example, we can use structured outputs to do exactly that. Also, if we already know the types of answers that we want from the models, we can tell the model to use the specified tokens. So if we already know that we want to know if something is true or false, here we can make the model only generate those 2 tokens. So it's going to be very easy to then parse the answer and know what the model answered. So for example, if we see this example here, this string that says the meeting is Monday at 1 p.m. with François, the structured answer output would be here a JSON schema with the correct or like the most important information of the string above. So if instead of having to deal with strings with characters and having to parse that string and not being sure what's in the string, if all the information is included here with the JSON, it's very easy to parse because we already have libraries that can parse JSON formats. And then it's going to be very easy to know exactly what type of information is missing. Yeah, it's going to make working with LLMs way more easier. So just to summarize, the advantages of using structured outputs is number one, the consistency. So if we choose to work with JSON schema, then all of the answers will have to follow that format and all the answers will be then consistent. It's going to be very efficient because we no longer need to parse strings, for example. It's going to be way more reliable because we can see if a value is missing or if the model actually answered with the complete information we wanted. And so when should we use structured outputs? Well, for example, it's very useful if we want to extract information from a paragraph or just unstructured text. So here we can get JSON schemas like we see on the screen where we have exactly what type of meeting, the time, the date, and who is going to be included in the meeting. It's also very useful when we want to integrate our apps with external systems. So let's say I want to use a web search API like Bing Search or Brave Search API. Then it's going to be very easy to use structured outputs in this case because I already know the fields I want to send to the web search API. And I already know all the other attributes, all the other options I want to send to the API. So here is very easy and very convenient to already get from the model, from the response, the correct request that I can send then to the web search API. And it's also very useful when you want to create structured content. So for example, let's say you want to write financial reports and you already know that you want an introduction or some type of analysis and then a conclusion. Then you can use structured outputs to make sure that all the sections are included in the model answer. And it's going to be very convenient to use in the structured outputs in this case. How can we obtain these structured outputs? Well, there's two main methods that people developing these models do to allow us to use structured outputs. The first method is simply to train the model to do it and also include the instruction within the prompt. And the second method is to use what we call grammar-based constraints or context-free grammars to constrain the type of tokens the model can output. So I'm going to dive deep within these two methods. But before I do that, I just want to specify that these two methods can be actually combined. And when we use most LLM providers, they gives us access to both methods, for example. Here, OpenAI, we already know that we can use method number one and method number two. So actually, we don't see the method, we just use structured outputs, but in the background, that's what is happening. And to make it easy to get structured outputs, then we can use tools like Pydantic if we are working with Python, for example. to easily create the JSON schemas for the types of answers that we want to see in the response. So I'm going to just give a little bit more details for each method. So the method number one, which is just to fine tune the models to produce JSON schemas. Here, OpenAI or whoever is training these models just has to create a data set of prompts. So, for example, respond or extract the information within this text, and I want the answer to follow a specified JSON schema. And then that will be in the input, and the output will just be the JSON schema with the correct information. So if we train the models to do that with all of those examples, then the model will learn to do that. So, for example, here, we want the model to extract the information of the string. The meeting is Monday at 1 p.m. with François. And then we give it a JSON schema that is empty with the fields we want to see in the answer. Then the model will be able to fill in the values, and we will have the completed answer, the JSON with the correct values that we want to see. Now for method number two, that uses grammar-based constraints. Here, we are not training the model to do it. Here we are mainly restricting the model's choices for the next token. So on top of the model, let's say, we are removing all of the token options the model can generate. And for example, if we want only the tokens true or false, then the model will only have the choice of using those two tokens. So this is something that ensures that the answer will actually follow the instruction or follow the format at a very reliable rate. It's going to be basically good all the time. So here, for example, we have an LLM, and we know that LLMs produce probabilities for the next token. So let's say here the LLM for the next token will be, the next token here will be here at 22%. What we can do is to apply a mask, and here put all the other tokens at 0 and only leave the probabilities of the token that we want to see in the answer. So for those two tokens, the tokens false and true, we leave the probabilities as is. And since we put all the other probabilities to 0, then here the token that the model will generate, or that we basically here the token that will be chosen by default is the highest number. And since all the other ones are at 0, then false will be the next token that the model would generate, basically. And that's what we call constrained sampling, because we are constraining the number of tokens that the model can use to output a response. And to do this ourselves, we need to have access to the probabilities of the model. So this is very easy, or easier to do with open weight models, because we have complete access to those probabilities. We know exactly what's happening in the model. But for closed source models, not every company is willing to give that information. So for example, with Gemini or other companies, it's not something that we can do ourselves, this method of grammar-based constraints. This method can become actually very complex. So let's say the model generates these 3 function calls at the same time within the same answer. Then the model has to make sure that the brackets are correctly in the right position or in the right order. The commas, everything has to be in the correct order for these tool calls to work. So doing this constraint sampling method can become very complex because you have to keep track of what you generated before to make sure that you actually complete the string, you complete the bracket, you complete the values correctly. So to make it easier, or one way to do it in an easy way, is to use what we call context-free grammars. So this thing is the context-free grammar is basically a list of strict rules that the model will need to follow when it's generating a response. So for example, I want to make sure that the rules will constrain the model to only generate a valid JSON. So here I put a very simple example of what these rules can look like. For example, here I start, and then the next token will need to be a greeting. And here the greeting is defined as hello or hi. So here the model has two available choices, and the model will choose depending on what has the highest probability. Then the greeting is followed by a comma, then by a space, and then by a name. And then here name is also defined by two strings. So there's Alice and then there's Bob. The model will choose whatever has the highest probability, and then we will end the answer with the exclamation point. So this is what we call a strict rule or a context-free grammar to have an answer that follows exactly what we want to see in the answer. Then after we define the rules, we need a decoding algorithm that follows the progression of the text according to this grammar. So for this decoder, it can either be a parser or a finite state machine or an automaton. And at each step, so while it's answering, only the tokens that follow the rules will be allowed for the model to use. And I'm not going that much into the details because this process or these algorithms are already implemented and are very fast already, entirely automated. And you can use them when you use, for example, libraries like Outlines or Llama CPP, or even the Open API if you're using one of the OpenAI models. So behind the scenes, these libraries will create the grammar, the list of rules to follow, and then have a decoder algorithm that will make it so that the model can only output the tokens it needs to output. So if you want to see a complex JSON response with many indented keys or many layers, then the model will have to follow the rules, and then at the end you will have an answer that actually follows exactly the rules that the library set at the beginning. I just want to say that different implementations can have varying speeds, and for example, Outlines, their implementation is quite faster than the OpenAI one. So that's interesting to note. And so if you're mainly using open source or open weight models, then I recommend you use Outlines. If you have to use OpenAI models, then yeah, you will have to use the OpenAI implementation. Then you have libraries like Instructor that will use whatever implementation is already available from the different providers. Instructor is very useful when you are defining the different JSON schemas that you want to see in the answer. And I will come back to this in the coding example. So how can we use these methods in practice? Well, like I said before, we need to specify the answer we want to see. And to do that, we can use libraries like Pydantic if we are using Python. So what's Pydantic? So basically, Pydantic is a Python library that can help us define and validate data models. For alternatives, you can look at Zod for JavaScript or libraries like Fluent Validation for C#. And so what does it look like when we use Pydantic? Well, basically, here we can create what they call a base model. So let's say I want to create a user. I give the user an ID and I specify that it's an integer. And I also say that this user has to have a name and this name has to be a string. So then I can create one user with an ID and a name. And then I have the final Pydantic typed object. This is very useful because then it's going to validate that the ID is actually an integer and that the name is actually a string. Then when we create this class, this user, we can then use the Pydantic library model dump JSON to create the JSON representation of an object or a base model. So this is going to be very useful for defining the LLM answers. So for example, I can say, I want to see what type of event, the date, the hour, and the people that will be in the event. So let's say I have this. I can then pass the JSON representation of this base model, this event, and I can prompt a model to answer me and to put the information in the exact format that I am specifying. And when I get the answer, here Pydantic can validate that the LLM answer actually follows the schema, the types that I set above. And it's going to be very useful for that. So if I show you a complete example, here I'm showing something that's already in the OpenAI documentation. So here I have a calendar event and I want to see the name of the event, the date, and a list of participants. And I'm actually also giving types for each attribute, each variable that I want to see in the calendar event. And then when I make a request to get an answer from OpenAI, I can then give it the instruction. So for example, extract the event information. I give the model the string that contains the information I want to extract. And then within the same API call, the same request, I also give the model, the system, the calendar event. So this is the Pydantic object that I defined here above. And when I receive the answer here in the event variable, I can then easily access the name, the date, and the participants variable within this response here, the event. So this is very useful when you're working on top of these LLMs. So now I'm going to show a quick example that it is basically the same thing, but here instead I'm going to show how to do it with the instructor library, because it's very easy to then swap whatever LLM provider I'm using. So here, this is a notebook and I'm using Colab to run the code. If you don't know about Colab, it's very useful for these kinds of demonstrations. So here, first I'm going to show you the text that contains information. And from this text, unstructured text, I want to extract specific information that I want to then either save to a database or to do some type of analysis or whatever. I just want to, from this text, extract the relevant information that I want to see. So to do that, I'm going to use Pydantic and I'm going to For example, I will define a person object, Pydantic object, and then this person will have a name with a string, and the string, I want the size of the string to have a maximum length of 50 characters. So this can be very useful if you are validating that the information that is extracted is correct. Then I want to see the age. So there's the age can either be an integer or a string. This is just for demonstration purposes, because here I will either want to have everything in integers or everything in strings. It doesn't make sense to let the model choose the type within. So yeah, here I'm just giving a choice. Then for the role, I want it to be a string, and then here I'm giving it a description. So this is very useful because sometimes if you're giving this information to the models, the JSON schema that is empty, sometimes the models don't know exactly what information should be in the key. So for the role key here, I'm specifying that it's the role of a person within a company. And I also give it an example. So for example, a developer. Then for the company, here, since I know that I'm working within a specific number of companies, for whatever reason, I already know the number of companies that will be in the text. Here I can specify the list that the model will be able to choose from. And if a company is not within that list, then the model can choose to put the other string for as answer. Then, as we saw in the first session, it's very useful for non-reasoning models to instruct them to reason before they answer, to think step by step before they actually answer the question or the instruction. So that's what I'm doing here. I'm forcing the model, I'm telling him to write a reasoning string, to write how the model needs to approach, how it will approach solving this task. And finally, here as second key, I want the actual people list. And this is going to be a list of person, which I defined here above. And I want a minimum of actually three people. Here it's because I already know that in the text, there's three people that are mentioned in the text. So now for the second step, once I finish defining the Pydantic models, then I can create the API client that I'm going to use to make the requests. Here I define the text, the unstructured text. And here as fourth step, I write the prompt. So I say to the model, extract all the people mentioned in this text. And I put the text in the prompt here as a variable. And here on number 5, I make the requests. And here I display the answer. I just want to specify that I used Gemini 2.0 Flash. So this is a very cheap, very small model that you can use. And here for the answer, we can see the people extraction variable that the model answered with. We can actually, with code, see all of the keys that are defined above, all the variables. So if I go to the reasoning, I print the reasoning, I can see that the model said, I will extract the name and the age and the other things. I will iterate through the text. And if the company does not exactly match the list, I will use other. And then I print within this for loop all the different people that the model extracted. And I can see for person 1, I have the name, the role, the company, the age, or I can also have the string representation of the same information. So as you can see, using structured output, working with LLMs is much more easier than trying to parse the unstructured answer from the models. Here I'm able to directly see how many people, what the different attributes of all the different people. I can make the model think before it answers. I can do basically everything that I can do without structured outputs. But here I'm using structured outputs to actually make it very easy to work in code with LLMs. So as you can see, it's very, very useful to do. Now, if I show some more base model examples, so let's say I want to extract the location information from job posting. So let's say you have a job posting on LinkedIn, for example. If you're looking at job postings, you see a lot of unstructured text, a lot of information. And if you want to, for example, extract key things from unstructured text, then you can use, like I showed, Pydantic to define the information you want to see. So here I'm just showing an example of trying to get locations from job postings. So here I have the chain of thought attribute, the variable that will contain the step-by-step reasoning of the model. Then I want to see a list of cities, list of regions. I specify the type, so list or string. I specify the number of items the list should have. So for example, I want to have at least one item in the list, one element. I show examples, I show description. So all of this is just extra information so that the model can extract the correct information and put that into a JSON schema. So everything here is just to make it easier for the model to actually, so that the model is able to extract the information I want to extract. So if we have the salary, for example, we want to know exactly what salary is given by each job posting. We can do the same thing. So we have the reasoning at the top, is because the model generates from top to bottom. So that's why it's always at the beginning of the answer, basically. And for the salary, we can either have a list of floats or strings, because sometimes the information is not contained in the structured text. So we want to give the model the choice to put if the salary information is not present in the text. Then I have more example of using literal. So this is something specific to Python, but here I'm saying to the model, these are the options, so that I don't see different types of answers that later on will be harder to work with. So if I'm already know that I want to see hourly, monthly, annually salaries, then the model will not try to come up with other time frames for salary, for example, like a daily salary or weekly salary. I don't want to see that. I want to see hourly, monthly, annually. And then this is where I make the request. So here would be the Pydantic model that I defined above. Here is the prompt with the query. So the query here will contain the unstructured text that contains the information, the paragraph, the page, the whatever information you have. And yeah, that's how you make the request. And just to show you quickly, I recommend you check out all of these examples if you want to learn how to use unstructured outputs, because yeah, it can make working with LLMs way more easy. besides using, frameworks, more complex frameworks. So let's go to RAG. So in the first section, Louis talked a lot about how we can implement a RAG system within our applications. And here I just want to show with simple examples how we can implement such systems. We're not going to show a complicated or complex examples, but it's just to show you how simple it can be, and quick it can be using Python or some other library. So if I show an example that uses the Google Gemini API, so here, let's go to the top. Here I will be using two APIs because the LLM I'm going to be using is actually Gemini. But in order to create these vector representations, these embeddings, I'm going to use an embedding model created by OpenAI, and we can access it by doing API call requests. And so that's why I'm setting, I will be setting two API keys and not just one. Then here I'm just importing all of the data that I want to work with. Here to just put some background context. We want to build a chatbot that is able to look at different articles that talk about the Meta Llama model. So if we have questions about the Llama model, then this chatbot needs to look at those articles, see if the information is there. And if it's there, I want to see that in the final answer of the chatbot. So here I'm just downloading these articles locally here in the Colab. And we can see here that we have actually 14 articles. And if we actually split those articles into chunks, we have 174 chunks. Just to make it clear, here is our chunking function. So here basically we divided the articles by chunks of 1,024 characters. So this is not the optimal way to go about it, but it's one way to go about it that is very simple and works in most cases. But yeah, this is very, keep in mind that this is just for demonstration and just to show quickly how we can build a chatbot. Now, once we have the articles that are chunked, now I want to create here for this demo a pandas data frame. And I'm going to put all of those chunks within a single column. So let's imagine that within my pandas data frame, right now I only have one column, and it's the chunk column. And for each row, I will have all of the different chunks in my dataset. Then here I'm defining what is the get embedding function. Here we are going to be calling the text embedding tree small model, which is a very small model from available in the OpenAI API. So this embedding model just needs text, and it will output an embedding, which is just a list of numbers that represents this text specifically. So what we do here is we just loop over all the rows, and then we create the embedding for each chunk in the data frame. So now we have two columns. We have the chunks columns and the embedding columns. So for each row, we'll have the text, the strings, and the embeddings for each one of those chunks. Now, if we write a question, so for example, I write, how many parameters does llama 2 has, and then I get the embedding of the question I just wrote. Then I can see exactly the number of values that are within this embedding. So we have 1536 number of values for that specific question. So this will not change. This is specific to that embedding model. This is the number of values for each vector representation, the number of dimensions in the output. Now let's show how we can use cosine similarity. So here I have two questions, and I have, for example, the sky is blue, and llama 2 model has a total of 2 billion parameters. So these are two different strings. Now let's compute the embedding for both questions. So I will have two embeddings. And now using the cosine similarity function, which I import from this library, I can see the similarity score of the question with the question embedding and the question above. So, okay, so we have this question embedding, the how many parameters llama 2 model has, and I compute the score of this question above with the two answers below. And we can see that for the answer, the sky is blue, we can see that the score is actually really, really low because the answer doesn't match the question within the embedding space. And in the contrary, for the answer, the second answer here, we have a high score for the similarity of 83%. So this is just to showcase that similar pieces of text will have a higher score than two pieces of text that don't mean the same thing, basically. Now, if I do the same thing of taking the question and comparing that to each of the chunks in my dataset above, then I will have actually 174 scores logically, naturally, and I will be able to sort the answer to get the chunks that get the higher score for my question. So I can print the indices that have the highest score, and we can see that the chunk with the index with these three index, these three chunks actually have the highest similarity score. If I print the chunks for each of those, we can see them here, and one of them should contain the answer to my question. Now, when I build the request, this is basically the chatbot right now, the RAG chatbot. Here I have the system prompt, I have the prompt, I have the model that I want to use, and I have basically the request to Gemini. Then if I print the request, I'm going to see the answer. So llama 2 is available in 4 sizes: 7 billion, 13 billion, 34 billion, and 70 billion. This is basically what a RAG chatbot is. So basically here I have the question, I filter the indices, the chunks that have the highest similarity scores. Then I take the text within those chunks and I just append that to the prompt. So within the same prompt, I'm also adding the context that contains the information. And then because of that, the chatbot will be able to answer me correctly. So this is a very, very simple example of what a retrieval-based system looks like. You do the retrieval, you get the text, and then you add that to the prompt so that when someone asks a question, then the model can check the information in the prompt, in the context, and answer correctly. So here I have another chunk with some information that wasn't in the articles. Here I ask how many parameters the newer model has, the model 3.1. Here I add this example chunk in the prompt. So this is the correct information taken from the meta documentation. And we can see that we get the correct answer here once we do the request. And if I do the same thing without adding the correct context, then we can see that the model is not able to answer me because when it was trained, it didn't have that answer. So we can see that by adding the correct context, these models are able to read the context in the prompt and answer reliably. So this was a very basic example. Now let's look at the same example, but now let's use a framework. There's many of them. You can use Llama Index, for example. They specialize in retrieval for these exact purposes, for these kinds of chatbots. So if I do the same thing, I download the dataset, I open the CSV files with the 14 articles. Here, I'm going to create what we call Llama Index documents. And I'm going to put all of the different content of the articles within each document. And each document has a text attribute. So I'm just putting the content of the articles in the text variable. And here I'm printing the contents of the first article. And this is where I create the index. So this is what we call a vector store index. Here, Llama Index makes it very, very easy to create one from a list of documents. So here I'm just specifying the list of documents that I want to use. I'm saying exactly what the chunk size should be, what should be the chunk overlap, what should be the embedding model. I just want to specify that these options should be optimized based on evaluations. So here we are just showing how we can create very quickly a vector store index, but the next step would be to try to optimize it. So once we have the index, we can then, so this is going to be very quick. And then once we have the index, we can specify the model that we want to use for the answer generation. Then if I do a quick test here, I do a query using the index as query engine. I ask a question, so how many parameters Llama 2 has, and it's able to answer me correctly. And if I ask a question about Llama 3, then it's not going to be able to answer me because the articles above do not have the information for Llama 3. You can see that to create the same chatbot as I showed in the other notebook, here it was really, really easy to create. But as I said, the next step that we are actually going to show in the next session will be to evaluate and iterate over this RAG system. Now, what embedding model to choose? Well, there's many different embedding models. Ideally, you want the embedding model to know about the type of data that you are working with. So here I'm just showing a list of models taken from a leaderboard. You can try to use some of them. So as you can see here, there's Gemini embedding model that is okay. Then you have the Snowflake embedding model. You have many different ones to play with, to try. But as I said, to really know what model you should choose, you need to evaluate your system to know exactly the scores that your retrieval system is able to get. And also, it can be very beneficial to actually train an embedding model, because sometimes the type of data that you have is not in the training data that was used to train these open public models. So some of them actually can be fine-tuned. So that will be like a different optimization avenue if you want to increase your retrieval scores. But we will talk more about this in the next session. So, like I said, it's good to look at the leaderboards, but it's way more useful to actually evaluate those systems. So we'll want to measure things like the precision of your retrieval system, the recall of your RAG app, the recall MRR, and other measurements if they are relevant to your task. So now let's change topics. Now let's look at context augmented generation, which is the same thing, but here we are mostly talking about bigger contexts. So let's say you have a book, or you have a big number of documents that will remain the same. Here, using CAG will be very useful. So different providers make the functionality available. You have Gemini context caching. So, for example, if you have a specific number of PDF documents that you want to cache in the system, you can do so and just pay by the number of tokens in those documents. The default time that the content will be cached is 1 hour, but you can specify that in the API. Then you have automatic systems. So for Gemini, it was manual. You had to specify, these are my documents, I want to cache them. Here with OpenAI, it's done automatically. So whenever your prompt is above around 1,000 tokens, the system will automatically cache the prompt, and the cache will remain active for at least 10 minutes of activity. So it means that if you ask a question with a long context, and you ask the same context an hour later, then the system will need to recache the content in your documents. And you have anthropic prompt caching, which works similarly to the OpenAI prompt caching feature. Right now, they pretty much all have same type of features, and they really help in reducing costs, because once the content is cached, then you don't have to pay the compute for those tokens. And it's also something that can speed up the answers, so the latency can be reduced. If I show quickly how to use Gemini context caching, here I have a dataset that contains documentation from Llama Index, and it has 150K tokens. So this fits within inside the context window of Gemini at 150K tokens. Now here I'm going to create again a RAG bot using context caching without, and also comparing to a chatbot that doesn't use context caching. So here, that's why I'm creating Llama index documents. And here I will create, once again, an index and query this chatbot. And you can see that for the chatbot, it took 4 seconds to answer. So I asked how to set up a query engine in code, and it answered me in 4 seconds. Now let's do the same thing with Gemini context caching. So here I create the file upload. So here I'm converting the JSON-L file into .txt because at the time it didn't support JSON. I'm not sure if it's the case right now, but basically it's the same content but in a text file. Here I specify the model that I want to use for the cache and later for the chatbot. So I create the cache. First, I upload the document, and then I create the cache using this Gemini SDK for the Gemini API. And here I'm going to ask a question using the cached tokens. And I also say that I want a maximum of 1,000 tokens for the answer. And I can see the answer. I can see the metadata of the answer. So in total, we have 200,000 tokens used. Actually, the number of tokens cached was actually 200,000. So it different from the file name because it was using a different tokenizer, basically. But it shows that here it answered me in 2 seconds instead of 4 seconds. So we can see that it started answering me way faster than the Llama Index chatbot that didn't have the context cached. So this is just an example of using context caching. Now, how can we fine-tune LLMs? As Louis said, it's something we choose to do mostly after we have tried optimizing everything else. So when we don't have really the choice, we actually go into trying to fine-tune a model. And to make things even easier, we can start with closed source models if we can use closed source models. If the data can be shared with OpenAI, or if the company we are working with actually allows to use closed source models. And here, to make things easier, we can actually use the services that are provided by these closed source models. So for example, we can use the OpenAI platform. And just to put some context on what we want to do, let's say we have a system, we have an AI tutor that is able to answer questions regarding documentation of various AI libraries. So let's say Hugging Face, Llama Index, LangChain. Right now, the system is using GPT-4o and then some retrieval to be able to retrieve the correct information, add that to the prompt, to the context of the prompt, and then get answers that have the correct information. So right now, the system is working pretty well. It gives us complete and useful answers. But now we wonder, what if we use GPT-4o mini? Can we have the same quality of answers? And if that's possible, if we get the same level of quality, then we can save a lot on tokens, on costs for the system, basically. So now let's see how we can actually use the OpenAI fine-tuning service. Here I basically already created the dataset for the fine-tuning example. So basically we have a JSON-L file with an input and an output. We have questions, and the answers, the output, is written by our current system that uses GPT-4o. And that also includes the retrieval part done before. So here we already have that data set of questions and correct answers. And we want to fine-tune GPT-4o with this data set. And here, the only thing that we are doing here is downloading that data set from Hugging Face. So right now it's stored in Hugging Face, and I am downloading it here in the notebook. Now, if I create here again a quick chatbot using Llama Index, I can see that it's able to answer me. So I create the vector store, I create the LLM, and then I create the query engine. We can start asking questions and see the results. And we can see the sources used for each question. So here I have all of these chunks. Llama Index calls them nodes, and each chunk, each node has a URL, the URL that points to the correct content, basically. So this is useful because then I can cite whatever information the model is using to answer. I can tell the model, please cite your answers using the URL, for example. And then people can then click on the URL and confirm that the information that the model answered with is correct. So here I have another question and another example. Here I'm just validating that the dataset is in the correct format. This function validate dataset will validate that my dataset contains the key messages, the roles, the content. So this is important because we want the inputs to be assistant or user inputs. So this is the role key. So this is just basically making sure that the dataset has the correct OpenAI format. So this is not important to memorize. Here, I'm just counting the number of tokens in each example, each sample. And here is where I will format the dataset. So this is what I was talking about. My dataset that is currently stored in Hugging Face and right now in the notebook has questions and answers. But I want my dataset to fit within the correct format that OpenAI needs for this dataset to work for the training run. And so I'm converting basically every question and answer into this message, into this JSON object. And at the end, I'm going to have a JSON lines file where each line will be a JSON with this exact content. And so I'm going to basically prepare the dataset and upload that to the OpenAI fine-tuning service. So you can either go directly in the OpenAI fine-tuning service and drag and drop your dataset, or you can actually do it with the OpenAI API. You can use code to upload your file to the fine-tuning service. So let's just go back to the presentation. Here I have some screenshots to make it easier to follow. So here we are going to go to the platform. So you see the URL, platform.openai.com/fine-tune, or you can go to the fine-tuning section here in the platform, and then you're going to create a new fine-tuning job. Here you can basically choose which model to fine-tune. So you can fine-tune, here in our case, we want to fine-tune GPT-4o mini, so that's why we choose that. Then we select an existing dataset. So you can either, like I said, upload this using the website, or you can do it in code using the API. Here we can also specify what is the training data and what is the validation data. So this is, whenever you are training AI models, you need to measure performance, and you cannot measure performance on the data you are training with, because of course the model will get better on the training data. But the point is that the model needs to learn how to generalize to other types of questions. So we need this validation dataset, which contains other questions that the model will not see during training. And we want to measure the performance on that validation dataset. So here we also specify what will be the suffix. So when we will use the model afterwards in our application, instead of putting GPT-4o mini / and the rest of the string, we will use this string but also append the suffix so that we can use the fine-tuned model and not the general one. Then here we need to set the number of epochs and batch size and the learning rate. These values are given to us automatically, but during training, during our experimentations, we will try to optimize them to get the most performance. So usually you don't train one time, you actually train multiple times and you play with these values to actually try to get the most performance, the highest score, the lowest loss on your validation evaluation. So once finishes training, you will have this succeed status, and you will be able to see the graph of the loss, the training loss, and the validation loss. As I said before, you want to mainly look at the validation loss because these are the questions the model never got to see. And also you can see that for the training loss, it's usually a little bit lower because, of course, the model got better on the questions it actually saw during training. So this is just one training run, and you want basically to make sure that you have the lowest loss possible for your task. And I think that's it. Here I'm just, yeah, you can also check on the status of the training job in code. You can look at the OpenAI API. It's very simple. And you can start using actually the model directly with the API. So this is not very important, but yeah, it was mainly to show you how easy it is when you train these models using services like the OpenAI one. It requires a little bit more complexity when you're dealing with open source, open weight models, but yeah, it's basically the same process. But we recommend that you actually start with these services that make it a little bit easier to start with. And that's it for the second session. I hope you learned something. For the next session, it's going to be all about evaluations. So how we can take these chatbots, these retrieval systems, how we can measure the performance to actually try to optimize it for whatever task you are doing. So see you for the next session. Goodbye.
Before we end this, I just wanted to remind you that the full course is available on academy.towardsai.net for you to purchase. If you enjoyed the past 2 hours, please go check it out. On this, thank you for watching, and I'll see you in the next one.